Welcome to episode 17 of the Welding Codex. This is a podcast for those who want to learn more about the technical side of welding. Welding codes, heat treatment, welding defects, metallurgy, and all the subjects that your high school welding instructor didn't have time to cover. Like how I throw your high school welding instructor under the bus. Anyhow, today we have Gary Martin sitting in for Peter Kinney. In this episode, welding engineers Gary Pace and Gary Martin cover Clause 7 of AWS D1.1 Structural Welding Code Steel. Clause 7 covers stud welding. Gary Martin will be updating us on the changes between the 2015 and 2020 version of the code as we crawl through this clause. Anyhow, thanks for joining us. Before we get going, time for the advertisements. Got to pay the bills. If you're on a budget and looking for an online CWI course, check out train-eng.com. Traineng.com's Part A online course is $149. The Part B online course is $129. Train-eng also has the CWI course split out so that if you only have a few areas that you'd like to brush up on before the CWI exam, check out one of the buffet-style options. Train-eng has an online course that covers modules 6, 8, 9, and 10. This course covers module 6, metal properties, destructive testing, module 8, welding metallurgy, module 9, weld and base metal discontinuities, and module 10, visual inspection and NDE methods. All four of these modules are covered for $75. Also, Train-eng has a CWI Part A question bonanza that's $40. If you just want to go in there and take questions, go hit the question bonanza for $40. Also, if you like what we're doing here on this podcast, feel free to make a PayPal donation on my website, texasweldingengineering.com. Also, check out my YouTube channel. There's a whole bunch of material that I've been rat-holing on there for the last half a decade. Let's get into the episode. Thanks for joining us. Okay, welcome to the Welding Codex. Today we've got a special guest. Pete is out with the bubonic plague. No, he's got visitors or something, so he's out of commission for a while. So we got a friend of Pete's, another welding engineer, Gary Martin. I'm going to throw it to him, and I'm going to let him give an introduction of himself before we dive into today's material, which is going to be Clause 7 stud welding. Gary Martin, go ahead.
Hey, thanks, Gary. Appreciate it. It's going to be confusing since we both have the same first name. But yeah, I've worked with Pete for, gosh, I don't know, at least 6-7 years now on the AWS committees where I met him. He was actually my vice chair for the inspection task group and took over a few years ago. He may actually be in his second term by now for that. The chair served 2 3-year terms for a total of 6 years. So he was vice chair for 6 years, and now he's in his chairmanship. So also a fellow AWS grad, but a graduate school, not undergrad. I went to LeTourneau, and at the time, this was back in the late 70s and 80s, LeTourneau and OSU were the primary sources of engineering degrees with welding engineering actually on the diploma. There was a lot of other universities and colleges that had engineering specialties involving welding, but you got a mechanical or a metallurgical degree stamp on the diploma. So that's neither here nor there. I know you went to a different school, Gary, and I have a lot of colleagues that have gone to, Cal Poly and RPI and Carnegie Mellon, Ferris State, all had at one time or still have welding programs. I'm a very practical welding engineer, sometimes by force. I went to LeTourneau, and there was also a plant next door that R.G. LeTourneau started the college, and also a plant in Longview, Texas. And I worked about 2 years there, almost straight, both part-time and full-time during the summers, getting a hands-on welding experience, and then actually went to work there as the welding engineer for through the first 3 years of my professional career. And I've done a lot of other stuff, too long to mention on this podcast, so we should just jump on in the topic.
Right, and I guess bottom line is our substitute coming off the bench here to play center field for us is not a newbie by any stretch of the imagination. Gary brings a lot of code-related experience to the game, and our conversation. So We're glad to have you here. So, like you say, let's dive into today's episode and talk about stud welding. So, like any other of these clauses, first paragraph right out the gate is the scope, and it's going to tell you what it covers and what should be covered. So, 7.1, clause 7 contains general requirements for welding of steel studs to steel and stipulates specific requirements. Number 1 is for mechanical properties and material of steel studs and requirements for qualification of stud bases. For application qualifications, testing, operator qualification, pre-production testing, and workmanship. For stud welding during production, fabrication, erection, and inspection. And for stud manufacturer certification of studs and base weldability. Basically, this is my interpretation. This is like, clause 7 is like a code within a code, because stud welding isn't really arc welding per se. It is, but it's not. It's kind of its own special animal, but there's so much of this that goes on within the structural world that they couldn't really split it off, but it's its own code within a code. Any thoughts on that, Gary?
Yeah, I mean, at one time they thought about making a separate book on it, but it just didn't have enough content to make it worthwhile. Your next subject, strengthening repair, is kind of an oddity in that it has a clause in D1 and also its own book. So it may get there someday, but the same thing happened to rebar.
So 7.2 general requirements. Stud design. Studs shall be suitable design for arc welding to steel members with the use of automatically timed stud welding equipment. I might have to back up here for a little bit. Generally, where I've seen studs used is when you need something to grab onto concrete. I have a bachelor's degree in civil engineering, and my degree from Montana School of Mines is welding engineering. Doesn't say that it's welding engineering option. It's a cross between metallurgy and mechanical, but neither here nor there. With the stud welding, studs are usually put onto a beam, and then there's some kind of concrete poured onto it. So it gives it's an interface between the concrete part of a structure and the steel, the structural steel component. So that's why we've got to have, I guess, controls on how this is done, mechanical properties of the materials, the whole 9 yards. So this clause is what lays it out. So circling back around, 7.21, stud design. So it's gonna walk us through the stud design. With arc welding, basically what you're doing, or stud welding, excuse me, basically what you're doing is, it's like when you first start learning to arc weld, stick weld, it's basically getting the electrode stuck, but you're doing it intentionally with a specially designed electrode or stud. So you have it's like basically a big nail, and you've got like a gun, got some electricity flowing through it, and on the bottom of the stud you've got a little nubbin of flux to help keep the weld clean. And then an arc's initiated, the gun pulls the stud back and then jams it down into the weld pool, and you get a weld. Thoughts, Gary?
Yeah, so it's not quite like sticking a rod, and usually, but not always, there's a little ball of aluminum to act as both an arc initiator and a fluxing agent. The majority of the shielding or protection is served by the ceramic ferrule that is always around the base of a stud. So the initiation is, there's a solenoid in the gun. You pull the trigger, it establishes an arc, pulls it back a little bit to a preset amount, and then plunges it in after a timeout.
So, and then when he's talking about a ceramic ferrule, it's basically a chunk of coffee cup. It's just ceramic, and that keeps the liquid metal where you want it. Otherwise, if you didn't have that ceramic ferrule, that little piece of ceramic coffee cup type material holding that material in, it'd be a mess. If you've ever done one of these and the ferrule broke or whatever, it's really messy. So it makes it a nice contained little unit when it's done. So 722, 723, 724, it outlines, the arc shields, the flux, for flux 723, a suitable deoxidizing and arc stabilizing flux for the welding shall be furnished with each stud of 5/16 inch diameter or larger, studs less than 5/16 of an inch diameter may be furnished with or without the flux. So you've got some different parameters there. The stud bases, a stud base to be qualified shall have passed the test described in 7.9. We'll get to that. Qualified stud bases shall be used. Qualification of stud bases in conformance with 7.9 shall be at the manufacturer's expense. So there's going to be some of that done. 7.2.5 stud finish. That outlines how the studs need to be made. Any thoughts there, Gary?
No, not really. I mean, it had to be defined, so they just couldn't throw any material out there. But they just want it to be of good appearance for the observational quality of the owners and customers.
And then,
before we get too far along, you asked me to see if there was, we're working out of the 2015 code. There was a change. There wasn't a lot of changes to the Senate 2020 code, but one of them was back under what would be 9.21 under stud design. And before I get into that, I forgot to make my disclaimer that, because I am on the code committee, anything I talk about here, reference to the code is strictly my opinion, interpretation, and in no way reflects any official view or standpoint of the American Welding Society. But back to the new clause insertion has to do with manufacturer's ID that was inserted after what would be 7.2.1 in the 2015 code. And it says all headed anchor studs, and that is your concrete type of connection fastener, and deformed anchor bars shall have a manufacturer's permanent identification. Doesn't say where, it just says it's got to have it.
To give us some kind of traceability from, manufacturer to end user so that you can figure out who did what, and if something goes wrong, you can trace it back. Stud material, studs shall be made from cold drawn bar. These things, from what I've seen how they're manufactured, and this was 30 years ago, I went to a stud manufacturer in Chicago, but they're basically like big nails. They just are cold drawn. They start out with a big roll of wire, basically cold draw them and deform them and spit them out by the thousands. Not too much to that.
And what's interesting is in the bridge code, the bridge code borrows or steals a lot of content from D1.1 and then massages it, to meet the bridge requirements. And they have their own stud clause, but they call out a different material. This is ASTM 29, which is hot rot bars. They actually call out a cold drawn spec material. The tensile strength is similar though.
Right. And the difference between structural code and the bridge, if you've ever been on a bridge while there's traffic going across it, I did a few bridges in Oregon back in the day, but you'd be surprised when you're in a car, you don't realize how much of a bridge is bouncing when there's traffic going across it. So I think the bridge code, they have to bring into account a lot more dynamic loading and cyclical loading than maybe AWS D1.1 does. So there's some difference in materials between the two codes, but there's a lot of similarities too.
And the other difference, not to do with the content, but with the way the codes are formed, is that the every code book is a subcommittee of the main D1 committee. There's only one D1 committee, and all the books have a subcommittee. Well, D1.1 used to have subcommittees for every chapter of the book, and the bridge committee subcommittee never had that. So everybody on the bridge committee had to help write all 9, 10, or 11 chapters in their book, whereas in the D1.1 code for structural steel applications, there was and they're now called task groups for every clause in the chapter, whatever you want to call it, in the D1 code, D1.1 code. So you have more people generating, and that's why the language tends to be a little different, and also why D1.5 borrows that language, because there was a lot of work put into it, and it's still valid code for them.
A lot of similarities, but they tweak, like you say, they tweak it just enough to fit their situation.
Exactly.
Okay, base metal thicknesses, 727. When welding directly to base metals, the base metal shall be no thinner than 1/3 the stud diameter. When welding through deck, the stud diameter shall be no greater than 2.5 times the base material thickness. In no case shall studs be welded through more than 2 plies of metal decking.
So this is interesting because I also am on the sheet steel committee, and where sheet steel comes into play, of course, it handles materials that are thinner than the 1/8 minimum that the code is, the D1.1 code is scoped for. And so a lot of sheet steel is used in the form decking for concrete floored buildings, multi-story buildings. They lay out these corrugated panels, and those become the bottom form for the concrete to be laid in later on. And those are welded to the structural beams or trusses of that floor. And very often those are welded down with studs, anchor studs to anchor the concrete to the decking. And we refer to in the sheet metal code to this chapter in its entirety for anything to do with stud welding, but we now allow them weld through up to 4 layers of sheet metal, because if you think about, if you have 4 pieces of decking coming together at a corner, that's 4 thicknesses of that sheet decking that you need to weld through.
As you can see, if as you start wandering around the D1 universe, there's going to be some changes between the books where they massage things that, all right, does this make sense or does this not make sense? So like he said, for sheet steel, if you've ever been involved with civil engineering where the concrete meets the steel, you might come to a situation where there's 3 or 4 pieces that come together. So they give you a little more leeway than D1.1 does.
And just to back up a bit on this, the stud design, I don't think we mentioned it. 7252 kind of freaks people out sometimes, because the headed studs, or the concrete acre type studs that look like a nail, those nail heads are allowed to have radial cracks in them up to a certain limit, because that doesn't really affect their performance. And a lot of people freak out about that. They see the cracks, because especially when you get into much larger studs and much larger deformations, you're pushing the limits on the forging technique to keep those completely intact.
Right. Well, and forging is you're rolling out steel kind of like rolling out cookie dough, and there's going to be some discontinuities as you're rolling that cookie dough out, or as you're forming the head on the stud. So yeah, so they built into this code that, hey, it doesn't have to be absolutely perfect. Like if it was machined out of bar stock, they realized that the heads are been formed by a forging process, and it's like, okay, it's not the end of the world if there's a certain degree of cracking in there or deformation related discontinuities. All right, mechanical requirements 7.3. Standard mechanical requirements. At the manufacturer's option, mechanical properties of studs shall be determined by testing of either the steel after the cold finishing or the full diameter finishing studs. In either case, the studs shall conform to the standard properties of Table 7.1. We'll cover the Table 7.1 later on. So here it lines out the testing requirements. 732, testing mechanical properties shall be determined in conformance with the applicable sections of ASTM A370, mechanical testing of steel products. A typical steel test fixture is used similar to that shown in Figure 7.2. The engineer's request, as we've mentioned many times, the engineer has superpowers in this code. Upon request by the engineer from the contractor shall furnish the stud manufacturer's certifications, certified copies of the stud manufacturer's test reports, and certified material test reports from the steel supplier, including diameter, chemical properties. So, Gary, this is just giving us traceability, correct?
Exactly.
So, and if this is especially important. Well, I don't want to say especially, but I worked in the Hanford nuclear site, so everything had to have a cradle to grave type traceability on it. And bridges, and as we go forward in our world, you're going to need traceability. This isn't 1952 where we can just get by with maybe not having as much traceability cradle to grave as they had in previous generations. And I don't know why I picked out 1952, but
Well, another reason it's important is it's one of the duties of the inspector that you covered in a previous podcast to inspect the suitability of all materials used in construction. And the way he does that is looking at test reports. So if there's no test report, he can't determine the suitability of the material.
Absence of quality control tests. When quality control tests are not available, the contractor shall furnish a chemical test report conforming to 726 and a mechanical test report conforming to the requirements of 73 for each lot number. Unidentified and untraceable studs shall not be used. So if you have a batch of studs and you don't have paperwork on it, there's a workaround here. You can go get a chemical test done on it, take it to your local friendly testing lab and tell them you want this done, and get a mechanical test report done on them. And then you can move forward with that heat and lot number. Additional studs, the contractor is responsible for furnishing additional studs for each type and size at the request of the engineer for checking requirements. So, the contractor orders just a certain amount. Well, if the engineer wants to send them out for testing because he's got questions, the contractor is responsible for furnishing those additional studs. All right, what do you think? I'll let you dive into work 7.4, workmanship and fabrication, if you want there, Gary.
Yeah, so this is a very interesting clause. So I don't actually work on the task group for stud welding, but I do have a lot of experience with stud welding, and I'll talk about that when it's appropriate. But cleanliness in the entire code language has undergone some changes, but I think they missed it here. So in 741, it says, at the time of welding, the stud shall be free from rust pits, scale, oil, moisture, other deleterious materials that would adversely affect the welding operation. So in the other areas of all codes in the D1 community, they have dropped that word free. And it was a big brouhaha. The leadership of the code committee said, hey, everybody's got to institute this language and it has to be voted and so forth. And if you look you've probably already gone over it in fabrication, where it talks about preparation of base metal. It says something to the effect of there should be sufficient removal of these same contaminants to allow meeting the quality requirements of the code, is kind of a paraphrased version. But this actually still has the terms free from. And the problem that has caused over the years is you get a pedantic inspector, and he's going to do a white glove test on you and say, nope, I see residue on my glove. Or, he could go to all kinds of extents, microscope and swabbing and examinations, and say, nope, it's got to be surgically, free is free, absolutely none. So the code committee recognized that they had to change that verbiage, but I think they forgot that it was hiding out here in the stud area. So that's probably going to get changed in the next edition of the code to match the rest of the code books and the fabrication base metal clause. Coating restrictions, it says a stud base in 742 shall not be painted, galvanized, or cadmium plated prior to welding. So the stud base is that area where the arc is going to be initiated, and a part of the stud is going to be consumed into the weld. So you could, I guess, mask off that area and plate or coat the rest of it as long as the base is not affected. And then afterwards, if you have some kind of corrosion requirements where you have to, coat the rest of the weld, you do that after it's welded. I haven't really seen that many coated studs in use because, normally they're put in concrete and nobody sees them and they don't get that much moisture attack.
Right. And it gets back to, this is pretty much common sense with painted, galvanized, or cadmium plated. Those three words are just bad news or bad hoodoo in the welding world. That's just, those three items right there are just asking for some kind of weld related issues later on down the line, if you can even weld through it and get a quality weld, galvanized and cadmium plated especially. So base material preparation. The areas to which the studs are to be welded shall be free of scale, rust, moisture, paint, or other injurious material to the extent necessary to obtain satisfactory welds and prevent objectionable fumes. These areas may be cleaned by wire brushing, scaling, prick punching, or grinding.
So the intent was there, but they repeated the word free again. But what they really mean, to the extent necessary to obtain satisfactory welds. That's the intent of this rule, but the letter still comes out as free, absence of, complete absence of. So that's the second area they'll have to, one was the actual stud, and now the other is the area the stud is going to be welded to.
Right. And it's my interpretation. It means act like a grown up. Make sure it's clean enough so that you can get a weld down there. Other than the word free, and you could, like Gary said, is you could end up with a ultra zealous weld inspector that says it needs to be free. But for most of the world that I've worked in, it means, hey, get it somewhat clean, where a reasonable person could look at it and say, yeah, we see bright, shiny weld metal or whatever, and we're ready to go here. We don't have, dirt, rust, all kinds of crud on there. We can make a decent weld, and, a normal inspector without some zealous bent would be able to look at it and say, yep, that was done correct.
Now, this clause has brought up a lot of controversy in the construction industry because, as you know, construction takes place in all sorts of weather conditions, and there are experienced people on the code committee that says, hey, look, we welded through snow and rain, and you've got 2-3 plies of corrugated sheet decking, and it's got water between them. We've qualified stud through decking welds that were practically underwater and met the requirements. So what they do is they just make sure that's one of the exceptions in the contract documents to allow them to do that, because there still remains this prohibition of any moisture.
744 moisture, Gary.
Yeah, so this has to do with the arc shields and ferrules, and that's mostly just for safety, because if you get any moisture in those things and weld them, they'll tend to explode. So you want to keep those dry for that reason. It doesn't have really anything to do with affecting the quality of the weld, but they see the brunt of the arc force in the operation.
745 spacing requirements. Longitudinal and lateral spacings of stud shear connectors type B may vary a maximum of 1 inch from the location shown in the drawings. The minimum distance from the edge of a stud base to the edge of the flange shall be the diameter of the stud plus 1/8 of an inch, but preferably not less than 1.5 inches.
Yeah, so this is just sort of the tolerancing statement for placement of studs. They don't need to be that close to the engineering drawings. And the part about the edge is just so that if you have a stud that doesn't pass the initial visual inspection, there's a repair that we'll talk about where you can fillet weld it, and you need to have enough material left around that to tie in an adequate fillet weld to get the full strength.
And generally, when we're talking about putting studs down, if you've never seen this done, they just run along. If you got a 50-foot long beam or girder, you're going to put the stud welds on. They just crank them out and whatever spacing there is, and they'll just put 100 of them on there. So from a civil engineering calculation point of view, those things being off 1 inch or 1.5 inches or whatever, it's not the end of the world, because you've got so many of them along there tying the concrete to the steel that's why they give you such a big tolerance. It's not an aerospace tolerance because it doesn't need to be.
Yeah, and I've never seen anybody, go off by that far. I used to work in one of my first welding jobs in between school semesters was McCann Steel in Nashville, Tennessee. It's no longer there because that's where the Titan Stadium is. But we used to do a lot of stud welding, and we would lay them out, and they'd be on a common center line and then spaced down the beam or whatever we were stud welding. And then we would take a big sharpened punch and put a dimple right on the cross marks.
Arc shield removal. After welding, arc shields shall be broken free from the studs to be embedded in concrete and, where practical, from all other studs. So what's that entail, Gary?
Well, it's kind of funny that they allow that where practical for all other studs, because if the shield is still on there, it makes it awfully difficult to inspect the resultant welds. So I would say they need to completely remove from all studs, but I'm not really sure where that exception came from. And I guess for concrete embedment, you don't want any loose material around there. You want full contact with the concrete where possible.
747 acceptance criteria. The studs after welding shall be free of any discontinuities or substances that would interfere with their intended function and have a full 360-degree flash. However, non-fusion on the legs of the flash and small shrink fissures shall be acceptable. The fillet weld profiles shown in Figure 5.4 shall not apply to the flash of automatically timed stud welds. You want to run with that one, Gary?
Yeah, so that's a pretty loose criteria. You can have all sorts of things in you wouldn't accept in any other weld of that type, of fillet weld per se. And a lot of people think the code is only used for building construction, but it can be adapted to any steel product. And with the engineering exceptions, you can pretty much use it for anything you wanted to within the bounds of the material and the thicknesses. Even those can be accepted by the engineer. But the most experience I had with this code was in the wind turbine tower manufacturing fabrication. And inside a tower, you have all sorts of attachments for the decks, the ladders, equipment attachment points. And early, I guess when they first came out and up until about 2006 or 7, stud welding of a threaded stud was the way to do that. You had hundreds, maybe even thousands of these connection points inside a tower, and you attached, human safety type equipment, winches and ladders and tie-off points. And the problem is, you could look at a stud weld and it met the criteria, and then you put any kind of load on it and it snapped off. And I don't think anybody's using studs in towers anymore. They're using fillet welded threaded bosses. I had another tower manufacturer actually stud welded 1.25 inch internally threaded boss. I mean, that was a huge weld. They had like a 1,000 amp power source to do that. But they also had some failures, and they're like asymptomatic. You can't tell by looking at them. So we got to the point where we had an instruction to tap every threaded. You put a fixture on it and you bent it a certain amount to make sure that thing wasn't going to snap off. And they got tired of doing that, so they said, we're going to just fillet weld bosses to the tower.
Well, and my experience out at the Hanford nuclear site was for these. It was just for concrete, the interface between the concrete and the steel structure. But the way they test those is usually the inspector or whoever comes along with a big hammer, a big sledgehammer, and you just bonk it. And it's almost like a tuning fork. If it's connected correctly, it'll make a ringing sound. And if it didn't connect correctly, it'll either snap off or you'll hear this plunk or a really sick type of sound. But that's one way that they test them for those types of applications.
Well, and also the difference in those is the ones we were using were in a combination of bending and tensile, and those concrete anchors are strictly shear connectors. And there's a factor of safety, and you could have, a certain percentage of them completely non-connected or come loose, and you would still retain your design requirement for shear resistance in those conditions. But if you've got one or two studs holding on to a tie-off point, and one of them breaks, you've lost your safety factor, and you freak out the people that work inside towers. They'll never go up it again.
Right, completely different situation.
And you couldn't hit them with a hammer because you would damage the threads. So
threaded versus just a formed head, two different applications. Technique, automatic mechanic, or 7.5 technique. 751, automated mechanized welding. Studs shall be welded with automatically timed stud welding equipment connected to a suitable source of direct current electrode negative power. Welding voltage, current, time, and gun settings for all lift and plunge should be set at optimum settings based on past practice recommendations of stud and equipment manufacturers or both. AWS C5.4 recommended practice for stud welding should be used for technique guidance. So that just tells us what equipment we've got to use, and it tells you the settings and voltage, amperage, current, everything. Multiple welding guns. What do you got there, Gary? 752.
Yeah, I guess this happens. So they wouldn't have written about it. I've never actually seen it, but from a productivity standpoint, it makes sense. But it puts some parameters around if two or more stud welding guns shall be operated. That's kind of a strange phraseology. From the same power source, they shall be interlocked so that only one gun can operate at the time. So that's a good move. And so the power source has fully recovered from making one weld before another weld is started. Yeah, stud welding really taxes welding power sources. You often have a power source that is sized twice as high as the minimum need because it's a pretty quick duty cycle. There's not much rest in between, and it's a pretty high current demand. So you may see a 600 or 800 amp power supply for a 300 or 400 amp application. And if you push it, you can do it, but you're going to shorten the life of that machine.
Yeah, I've never been around situations where there's multiple welding guns, but it makes sense. You don't want stealing your buddy's electrical power while he's trying to do a weld, so you want to have a situation mechanically and electrically so that doesn't happen. 753, movement of welding gun. While in operation, the welding gun shall be held in a position without movement until the weld metal has solidified. That's just telling you you got to hold it as still as possible.
Well, not only still, but perpendicular as possible. And there's tooling on the gun to help you do that. But we found this to be the number one culprit for failed studs is when the operator was not holding that perpendicular. And on the inside of a tower, you don't have a flat plate. So the further you go up the tower, the tighter the radius gets, and that can be contribute to. He's kind of got to guess between the radius what's centered versus perpendicular.
You want to go with 754 ambient and base metal temperature requirements?
Yeah, so you probably went over this in fabrication, so the code wants to talk about the environment that you can weld in. And so basically not below zero, or when surfaces are wet or exposed to falling rain or snow. And again, that's a controversial topic, especially in the construction industry, when they have to weld under those conditions. And again, if you did, you just have the engineer make the exception or allowance, and you would do the proper qualification under those conditions to show that it would meet the quality requirements. And when the temperature of the base metal is below 32, it requires one additional stud in each 100 to be weld tested by the methods described in 7713 and 7714. Except that the angle of testing shall be approximately 15 degrees. So we'll need to look at those clauses to see what that entails, but it's basically the pre-production testing. And this is in addition to the first two studs tested for each start of a new procedure period or change in setup. Setup includes the stud gun, power source, stud diameter, gun lift and plunge, total weld, lead length, and changes greater than 5% in current and time.
So that's a lot to digest. And if you've ever tried to set one of these guns, sometimes everything goes well, and then other times things are less than optimum, and you might have to dial in one or more of the variables listed above, and that's why they give you all these variables. So then 755, Gary already touched on this. FCAW, GMAW, SMAW, fillet weld option. At the option of the contractor, studs may be welded using pre-qualified FCAW, GMAW, or SMAW processes provided the following requirements are met. You want to run with that from there on through?
Yeah, so there was a change made in the 2020 code. They changed the title of that to just fillet weld option. They didn't list all the process methods. It just said at the option of the contractor, studs may be attached with fillet welds using a WPS qualified in accordance with clauses 5 or 6, which should be in the 2020 code pre-qual or qualification. It just kind of rephrased that. You could really weld it with any of the approved process methods. That's used for repair of a stud, and you could, in fact, instead of using the automatically timed stud gun, you could physically just fillet weld the studs to whatever the application is. And then it goes into under that clause 755, you've got subclauses, and it talks about surfaces to be welded. And here again, here's another place where they've got to strike that word free. So it's repeating. It probably could have just pointed back to the previous statement. Here they're repeating code language already in the clause, which is a style guide no-no, because if you change, so they're going to have to, when they go and change this, they're going to have to look everywhere they use that terminology, and it looks like 3, maybe 4 places. So again, free from loose, thick scale, slag, rust, moisture, grease, and other foreign material that would prevent proper welding and produce objectionable fumes. So they're not only worried about the quality, but they're worried about the fumes. And if you look, each one has some different things added or subtracted or described differently as far as what's contamination. So they really got to clean that up. And the problem is this the stud welding sub task group. I think it has under 10 members. It's hard to get people to volunteer for these kind of specialized one-off groups. And usually you get a couple of stud manufacturers and then just some people off the street that are maybe welded a stud or two in their lifetime. So that's a topic of another podcast. Anywho, so 7552 stud end for fillet welds. The end of the stud shall also be clean. Just kind of seems obvious, an obvious statement there. Stud fit for fillet welds. The stud base shall be prepared so the base of the stud fits against the base material. Well, as you know, fillet welds rely on the shear connection, both components. And if you have a gap there, you're not getting that full strength carrying load capability of the fillet. So if you have a typical stud that has the chamfered end and the little ball of aluminum on it, and if it's a fairly large diameter stud, there could be a considerable gap at the perimeter of the stud base where, if it calls out a 3/16 quarter-inch fillet, you may only get an 1/8 inch of actual bonding to the stud. So you actually have to either grind those flat to fix them or have them made without that point in the little flux ball. 7554 fillet weld minimum size. So fillet welds to be used in minimum size shall be the larger of those required in tables 5.7 or table 7.2. So there is a minimum fillet requirement generally in the code, and that is so you don't get rapid cooling. Because if you make a teeny little fillet, you're going to get very rapid cooling and a brittle weld result or cracks. Preheat requirements of base metal to which the studs are welded should be preheated in conformance with the requirements of table 3.3. So that's just throwing you back to the pre-qual preheat requirements for the particular base metals you're working with. That was 7.5.5.5. 7556 shielded metal arc electrodes. Let me look at. Yeah, there were a lot of changes in the 2020 code, starting with 755 fillet welding option. I don't know how you want to handle that. Do you want to go through all those?
Yeah, we can.
Because practically everything in 7.5 was changed.
Yeah, go over and let's hit the high points of it.
All right, so this would be normally where 755 is. It's added 2 numbers in the 2020 code, the 955 fillet welding option. At the option of the contractor, studs may be attached with fillet welds using a WPS qualified quarters with clause 5 and 6. We went over that. And then it has 2 subclauses: production control, conformance to 9.7, which would be 7.7 in the 2015 edition, shall not be required for studs attached by fillet welding. So what that's saying is, if you're doing the automatic stud welding, you've got to do a certain amount of pre-production testing to validate everything's set up correctly. But if you're manually fillet welding, you don't have to do that bending and testing and pre-production stuff. And then stud materials, 9552, stud materials shall meet the following requirements. And this is, again, under the fillet welding option. Studs meeting the requirements of 926 or 726 shall be acceptable for use in pre-qualified WPSs. So that's just saying, as long as you get the prescribed material at the beginning of this chapter, you can use a pre-qualified WPS for it. Pre-qualification does not like using unspecified steels that aren't found in the code. That would throw you into a full qualification. And then the second item under that clause, stud material shall be considered Group 2 material for selection of matching filler metal strengths. So they want a little bit more strength than just the Group 1 materials, which would be like your A36 plain vanilla carbon steels. And then it talks about surfaces. So here they did make the correction. So back, instead of saying free, it says base metal. This is 7553 surfaces. Base metal shall be sufficiently clean to permit making welds that meet clauses 7.8 and 9.4.3. Studs shall be in accordance with 941, which is the free from language still. And the base metal shall be prepared to meet the requirements of 743 and 714.1. So it appears they looked at this, but they still missed the mark, I think, and they're going to have to do a little more changes. You have a comment?
Nope, go ahead.
Okay, 9554, which would have been 7554, stud fit. There's some underlying changes here. The base of the stud shall be prepared so that the base is in contact with the base metal. When a contact over the entire stud base with the base metal cannot be made, the following apply. So there's two clauses under that. The gap between the base material and the stud shall not exceed 1/16 at any point except as permitted below. So then you go to the second one. If the separation is greater than 1/16, 2 millimeter, the legs of the fillet shall be increased by the amount of the root opening, or the contractor shall demonstrate the required effective throat has been obtained. So that goes back to the old fillet weld rule that if you got a gap, you got to size up your weld to accommodate that. And they put a little more detail in that. 9555 or 755. And the old one, tack welds. No, they renumbered a bunch of that. They don't actually talk about tack welds in the old prior edition. 9555 is a new clause. Tack welds are permitted when required to facilitate installation. Tack welds should be comply with 7.17. And that's a fabrication clause. 9556, minimum weld size. So there it ties back into that, which we discussed. When fillet welds are used, the minimum size shall be the larger of those required in table 7.7 or 9.2. Preheat, the base metal to which studs are welded should be preheated in conformance with the requirements of the WPS. So it throws that back to the WPS, which if it's pre-qualified will come out of the appropriate table or whatever was qualified. 9558, welders shall be to perform fillet welding per clause 6 or clause 10. And repairs of fillet weld, 9559, repairs of fillet welded studs, fillet welds, 95510, visual inspection, all fillet welded studs and welded repairs shall be fully inspected in conformance with 8.9, which is the inspection clause visual.
Right, and that matches up with 7557 visual inspection of the 2015 code.
So now we're up to 7.6.
Stud application qualification requirements. 7.6. 7.6.1. Purpose. Studs which are shop and field applied in the flat, downhand position to a planar and horizontal surface shall be considered pre-qualified by virtue of the manufacturer's stud-based qualification tests, and no further application testing shall be required. The limit of the flat position is defined as 0 to 15 degree slope on the surface to which the stud is applied. Examples of the stud application that require tests of this section are the following. 1. Studs which are applied on non-planar surfaces or on a planar surface which is vertical or overhead position. Studs which are welded through decking. The test shall be material representative of the conditions to be used in construction. And 3, studs welded to other than group 1 or 2 steels listed in 3.1. Thoughts?
Yeah, that's just and there were some big changes made in the 2020 code here, but they're just saying if you do something besides flat, you've got some additional testing to do, particularly if you're going to be welding on group 3 and higher steels, or in the decking area, you want to test the actual conditions of number of sheets and thicknesses that you're going to be going through.
7.6.2, responsibility for tests. It just tells us that the contractor is responsible for performance of these tests. 7.6.3, preparation of specimens. It just lines us out on the test specimens to qualify applications involving materials listed in 3.1. Specimens may be prepared using ASTM A36 steel base or base materials listed in. So when you're doing your testing, you can use A36 or materials in group 1 or group 2. 7.6.3.2, recorded information. It just tells us what you need to do as far as recording the information. 7.6.4 is the number of specimens. So it tells you 10 specimens shall be welded consecutively using recommended procedure and setting for each diameter position and surface geometry. And tests required. 10 specimens shall be tested using one or more of the following methods of bending, torquing, or tensioning. Kind of jumped through some stuff there, Garry. What do you think?
Yeah, that just, and again, we're talking about the procedure qualification for the application of studs, not the qualification of the stud bases themselves, which is normally done by the manufacturer. That is a different type of testing and quantity completely. There were a lot of changes in the 2020 verbiage, starting back to what would be 761 or 961 in the 2020. It listed out that separated pre-qualified WPSs, studs conforming to 926, which are shop or field applied in the flat position to a planar and horizontal surface to steel base metals in groups 1 or 2 per table 5.3 are deemed qualified by virtue of the manufacturer's stud base qualification when welding is performed within the ranges of amperage and time of the manufacturer's welding recommendations. The limit of flat position is defined as 0 to 15 slope on the surface to which the stud is applied. For curved surfaces, the 15-degree flat position tolerance is measured at the tangent point where the stud is to be applied. Here again, studs in tower welds or any circular structural application. And then 962 is WPS is qualified by testing. So if you're outside of those definitions in 961, then you got to do qualification by testing. Examples of stud applications using mechanized welding that require test of this section are the following. So it lists 3 criteria: studs which are applied in non-planar surfaces or to a planar surface in the vertical overhead. So you can't pre-qualify vertical or overhead. Studs which are welded through decking. Test shall be conducted using the thinnest base metal thickness used in construction, but no thinner than ½ inch. A group 1 or 2 base metal, the same base material coating, and the thickest decking gauge and coating material used in construction. So when you're pinning down floor decking with studs, you've got to use what's going to be used in actual construction. And then the third item is studs welded to other than groups 1 or 2 steels. So if you're going with group 3 and group 4, quench and tempered steels and so forth, you've got to test on those materials.
And that's due to the as you creep up from 1 to 2 to 3 to 4, you're getting higher strength and they're getting to be more complicated materials to weld due to the preheats and the carbon content and the general strength of the material. So those are all taken into account here before they turn you loose to stud weld on them.
So the rest of that, I guess, paragraph 9.6 is the same. There were no changes made.
766, test methods. Bend test. So when you're doing this, studs shall be tested by alternatively bending 30 degrees in opposite directions in a typical test fixture shown until failure occurs. Alternatively, studs may be bent 90 degrees from the original axis. Type C studs, when bent 90 degrees, shall be bent over a pin with a diameter 4 times the diameter of the stud. In either case, the stud application shall be considered qualified if the studs are bent 90 degrees and a fracture occurs in the plate or the shape material in the shank of the stud and not in the weld. Thoughts?
So this brings up some interesting dichotomies here because they've talked about type C studs, and so far we don't know what that is. And they don't even tell you where to go look at that, and that's in that table 7.2, I believe. There's only 3 types of studs, A, B, and C, and they differ in tensile strength. And so obviously they go higher up. So if you've got a type C, which is the highest tensile strength, they want to make sure you don't bend it up too small a diameter. That would not be fair to the testing.
Yeah, and this gets back to a lot of times, you're just bending these. It's a destructive test. I don't know, destructive, but a mechanical test, and it's telling you, all right, you bend it 90 degrees and it's going to work. That being said, if you're going to know if it didn't weld right or if something's wrong, because it's not going to bend. If you're going to bend it over, if she's going to break, you ain't getting to 87 degrees and it's going to break. It's probably going to break long before then. So
exactly.
Tension test. Studs shall be tension tested to destruction using any machine capable of supplying the required force. So this is just telling you that you're going to have to do a tensile test on these. Tensile testing is the backbone of our engineering system for the most part.
Did you skip torque testing?
Oh, I did skip torque testing. 7662, torque testing. Studs shall be torque tested using a torque test arrangement that is substantially in conformance with figure 7.3. A stud application shall be considered qualified if all the test specimens are torqued to destruction without failure in the weld. Want to talk about torque testing?
Yeah, I tell you, that can be brutal as you get up in size. It can take a lot of torque to destroy a stud. So it's you're testing in all the forces that can be applied. So you're bending it over and you're pulling it straight out. But you can also do tensile testing in lieu of the torque testing, because the torque testing is really not testing the twisting resistance, but the actual tensile pull.
Right. And like you're saying, the torque testing works relatively well for smaller type materials, but if you get into some of the bigger diameters, like you say, the amount of torque that you're going to need to snap one of those things off is just outside the scope of what is generally able to be generated efficiently.
So that's why 765 says you can use one of the following. You can either qualify by bending, torquing, or tensioning. And you're going to go by the size of the really big studs are hard to bend. So then you might do a tensile test on that. And the torque test, same way.
767, application qualification test data. Application qualification test data shall include the following: drawings that show the shapes and dimensions of the studs and arc shields, a complete description of the studs and base material, and a description of the part number of the arc shield, welding position settings, record with which to be made for each qualification and shall be available for each contract. A suggested WPS PQR form from non-pre-qualified application may be found in Annex M. So it's just telling you what you're going to need there for the application qualification test data.
Yeah, so there's not a lot of leeway as far as variables here that you can get away with one qualification. You change the diameter or the material or the design of the ferrule, the end of the base, you're going to have to do another qualification.
Right. It's pretty open and shut case right there.
Yeah.
Production control, pre-production testing. Okay, so the difference between, I guess, once again, my opinion, stud welding and, let's say, just regular stick welding or any of the arc welding processes, before the shift, you have to requalify. If you were a qualified stud welder a day ago, it doesn't carry over to today because everything could have changed. So we've got to start a shift. Before production welding with a particular setup and with a given size and type of stud, and at the beginning of each day or each shift's production, testing shall be performed on the first two studs that are welded. The welding technique may be developed on a piece of material similar to the production member in thickness and properties. If actual production thickness is not available, the thickness may vary plus or minus 25%. All test studs shall be welded in the same general position as required on the production member, flat, vertical, or overhead. Thoughts?
Yeah, no, not a lot. Again, this is not my area of expertise, but it's similar to what you do for UT inspection testing. You have to do testing, calibration for testing every time, start of the shift and during certain other times. And because it's really hard, you can't really fully inspect a stud weld other than destructively. You can't UT it, X-ray it, and you really can't PT or MT it because it would fail all of them.
Right. And when you shift, when you start a new shift, when you get a new welder, when you change stud sizes, you got to go through all this and you got to document it. Well, as Pete and I have said, document. Production member option, instead of being welded to separate material, the test studs may be welded on the production member except when separate plates are required by 7715. Flash requirement, 7713. Stud shall exhibit full 360-degree flash with no evidence of undercut into the stud base.
So here's a point, and it was there's that term 360 degrees was mentioned elsewhere, and we were talking about that ferrule removal, and it said if you're not using the anchor head studs, you shall remove as much as practical for other studs. It kind of goes against this where you have to see 360 around that stud. You've got to remove that ferrule entirely.
Usually you go through, you have your apprentice or come in, follow, they get a chipping hammer, they take all that flash off, or not the flash off, the ferrule, they knock it all off, clean it up, maybe wire brush it for the inspector depending on what's going on. And it's going to give you an idea of how everything went. And things can get a little weird here with depending on the current and what you've got going on, because I don't want to use the term arc blow, but magnetically, electrically, depending on what your situation is on what you're welding, the flash from the arc can have a tendency to go in a weird direction. So you might have more on one side and less on the other if all the conditions aren't optimum. And I say this from experience, having it, and then you have to, move around welding cables and make sure that, you've got a better electrical and magnetic situation for the people trying to perform the work.
Yeah, so you can get arc blow in a stud weld. And the typical arrangement is, you're clamping a work lead somewhere on the structure. And then as you're going down, and you could be welding on a 40-foot long beam and have the ground clamp on one end. And as you get further away, you can get, that's current loss through that material. So you can get some changes to that operation and not realize it.
7714 bend test. In addition to visual examination, the test shall consist of bending of the studs after they are allowed to cool to an angle of approximately 30 degrees from their original axis by either striking the studs with a hammer or on the unwelded end, or placing a pipe or other suitable hollow device on the stud and manually and mechanically bending the stud. So that's just telling you that how you're going to deform these guys. And you're going to know if you just bend them over 30 degrees. Yep, they're good.
So no, that's not the same as the destructive bend test used for qualification. And that's why they allow you to do these pre-production tests on the actual production material, is because, hey, if it's an anchor stud and you bend it 30 degrees, you really don't even need to bend it back. It's going to serve the same purpose, but you can bend it back so it looks nice, and you don't have to waste any scrap material for your pre-production testing. Now, if you're using threaded fasteners, you're probably going to test them on a separate plate.
And you're right there. If you notice that when we said before, the studs before were bent 90 degrees, these are bent 30. So you're taking the other ones and bending them completely at a 90-degree angle to see if they're going to give you what you want. But here, you're going 30 degrees. Like he said, in 30 degrees, it's usually a shear connection, concrete, so you're still going to get what you need as far as from an engineering design. Then it's 7715, event of failure. If on the visual examination the test studs do not exhibit a 360-degree flash, or if on testing failure occurs in the weld zone of either stud, the procedure shall be corrected, and two more studs shall be welded to separate material or on the procedure member and tested in conformance with. So this is telling you what you've got to do in regards to if you fail. So then if either of the second two studs fail, additional welding shall be continued on separate plates until two consecutive studs are tested and found to be satisfactory before any more production studs are welded to the member.
Now, in any of your podcasts, I don't recall, have you guys been delving into the commentary?
No, we don't have. When we get to commentary, we're going into commentary.
Okay. So there's probably, I don't know for sure, there's probably a lot of commentary for this, and that one in particular. So in the event of failure, it says, okay, you failed, you got to weld two more. But what you better do is find out why they failed. So, and the reason for this testing is, construction environments are hard on equipment. Somebody could have dropped the gun, work lead connections and welding connections could have become loose. You could have a single phasing on the power supply, all kinds of things. And if you pass the test, the day before, and all of a sudden you're failing the test and everything else looks right, you got to start investigating. Don't just start welding another two, because you may be there all day trying to get that. You've got to look and see, check your equipment, check your connections, and then do your next test again.
Yeah, and I will say that as far as welding processes, when stud welding is running good and you've got everything dialed in, you can really just go like hell. You can put down a lot of studs in a relatively short period of time. But if things go sideways on you, there's a lot of different variables here that can really force a guy to pound his head against the wall trying to troubleshoot it and try and backtrack and figure out what's going on and how to get things back on the right track again. There's timing, there's amperage, voltage, plunge. There's a number of different variables that if you don't know how to troubleshoot this, it can really be a time-consuming mess trying to get it unkinked and moving in the right direction. Whereas stick welding, all right, you got 5 or 6 variables, travel speed, rod angle, blah, blah, blah. It's a little easier to troubleshoot, in my opinion, and try and get unkinked than this process, stud welding.
So there is about 3 pages of commentary for this clause, but there's not what I thought there would be on this particular paragraph.
So we were production welding. Once production welding has begun, any changes made to the welding setup as determined in 771 shall require testing in 7713. So if you make any changes, you got to redo. 773, repair of studs. In production, studs on which a full flash is not obtained may be at the option of the contractor repaired by adding the minimum fillet weld. So this is just allowing you, if you don't get the flash and you got something weird going on, as far as the arc flash, you can just have a guy come behind with a MIG welder or a flux core and put a minimum size fillet weld on there. Sometimes that's a cheaper option than troubleshooting it. And, if you're down to, your last 10 studs on this project and you don't feel like the easier, more cost-effective option would just be having a guy run some 7018 or something on the outside of those studs and deposit a fillet weld, sometimes that's a better option. That's what this is telling us.
Well, yeah, and the contrary to that, if you weren't going to do that, you've got to cut that stud off and then use a new stud in ferrule and then hope that, you get complete flash there versus, like you say, a guy using 3 inches of 1/8 7018 rod real quick, slap a little fillet on there and you're good to go. Because those studs can get quite expensive. Ferrules and so forth, if you got large studs, this repair is going to save you a lot of money.
Yeah, and then your second one or your third one or your fifth one or whatever, you could cycle through 10 of those trying to get them dialed in and maybe not need to get where you need to go. Whereas, like he said, just come in with a chunk of 7018, you're in a little bit of man hours there, but for the most part, you're good to go. What about operator qualification, 774? You want to go there, Garry?
Well, like you said, your qualification lasts a day. So you actually, the stud welding operator has to be qualified for every shift, essentially, is what this is telling you. The pre-production test required by 771 is successful shall also serve to qualify the stud welding operator. I'm not sure that's true. I think you are qualified, but if you have a guy run the test, he also becomes qualified.
Let me see here. The pre-production test required by 7 shall also serve to qualify the stud welding operator. Yeah, it does. Before any production studs are welded by an operator not involved in the pre-production setup, the first 2 studs welded by the operator shall have been tested in conformance with the provisions of when the 2 welded studs have been tested and found satisfactory, the operator may then weld the production welds. So yeah, you were right.
Okay, all right.
If it's when you're doing the pre-production test, if those are successful, then that says that your procedure is qualified for the day, and then that guy that made those 2 tests is also qualified. So, but it gives you a chance to get both of those. Kind of kills 2 birds with 1 stone, but you need to document it because this is a daily thing here. Whereas like when you qualify
welders for other welding processes like shielded metal arc or flux core or the other welding processes, it's forever. Well, as long as they're welding with that process. But with stud welding, it's a daily thing. You can have a guy qualified yesterday, you got to requalify him and do some paperwork. It's a daily qualification with stud welding.
775, removal area repair. What do you got on this one, Garry?
So if an unacceptable stud has been removed from a component subject to tensile stresses, the area from which the stud was removed shall be made smooth and flush, where in such areas the base metal has been pulled out in the course of stud removal. Shielded metal arc with low hydrogen electrodes in conformance with the requirements of this code shall be used to fill in the pockets, and the weld surface shall be flush. So there's another reason to do a spot repair rather than cleave off the stud and start over, because you may be in for a lot more work than just shooting another stud into it. And then further it says in compression, so that was talking about subject to tensile stresses in compression areas of members if stud failures are confined to shanks or fusion zones of studs. A new stud may be welded adjacent to each unacceptable area in lieu of repair and replacement on the existing weld area, C745. If the base metal is pulled out during the stud removal, the repair provisions shall be the same for the tension areas, except that when the depth of the discontinuity is lesser of 1/8 or 7% of the base metal thickness, the discontinuity may be faired by grinding it in lieu of filling with stud metal. Where replacement of the stud is to be provided, the base metal repair shall be made prior to welding the replacement stud. Obviously, replacement studs other than threaded type, which should be torque tested, shall be tested by bending to an angle of approximately 15 degrees from their original axis. The areas of components exposed to view in completed structures shall be made smooth and flush where the stud has been removed. So one thing is, particularly with an anchored stud, if you got a bad stud, just shoot another one next to it. You're good to go.
Yeah, you don't necessarily have to dig the other one off. And like you said, you could end up opening up a can of worms that you really don't want to deal with. So 7.8, fabrication and verification inspection requirements. Visual inspection, 7.8.1. If a visual inspection reveals any stud that does not show a full 360 flash or any stud that has been repaired by welding, such studs shall be bent to an angle of approximately 15 degrees from the original axis. Threaded studs shall be torque tested. The metal of bending shall be in conformance with 7714. The direction of bending for studs with less than 360 flash shall be opposite of the missing portion of the flash. Torque testing shall be in conformance with figure 7.3. So this is just giving us guidance so that if the flash doesn't go 360 and then you do the thick welding, it's just telling you which direction and how much to bend the stud. Additional tests, 7.8.2. The verification inspector, where conditions warrant, may select a reasonable number of additional studs to be subjected to the tests described in 7.8.1. So your third-party inspector, he might decide to just do 7 or 8 random tests and bend them over just to see. How about 7.8.3, bent stud acceptance criteria, Gary?
Yeah, so the bent stud shear connectors type B and the deformed anchors type C, and again, we're going to have to look at the tables to see what those entail, and other studs to be embedded in concrete type A that show no signs of failure should be acceptable for use and left in the bent position. So this tells us what I suspected before. You don't even have to straighten them out because they're still going to do the job. And when bent studs are required by the contract documents to be straightened, okay, so there's the exception. The straightening operation shall be done without heating and before completion of the production stud welding operation. Interesting. So if the contract documents allow it, you can leave them bent, but if they don't, you got to straighten them, but you can't use heat.
7.8.4, torque test acceptance criteria. Threaded studs type A, torque tested to the proof load torque level in figure 7.3 that shows no sign of failure shall be acceptable. So if you throw some torque on it in accordance with the torque level in figure 3, you're good to go.
Yeah, so note that's different than the destructive torque test in the qualification section. This is just to say, hey, put the load as prescribed by the table, and then if you don't get a failure, you're good to go.
Yeah, you're not taking it to destruction like in the other one. Corrective action. Welded studs not conforming to the requirements of the code shall be repaired or replaced by the contractor. That's common sense. The contractor shall revise the welding procedure as necessary to ensure that the subsequent stud welding will meet the code requirements. 7.8.6, the owner's option. At the option and expense of the owner, the contractor may be required at any time to submit studs and types used under the contract for a qualification check. 7.9, manufacturer stud-based qualification requirements. You want to grind us through that one, Gary?
Yeah, so this is a more extensive test to actually qualify the design of the stud, particularly the base and the ferrule combination. This entails a lot more testing, as you'll see. So the purpose of these requirements is to prescribe tests for the stud manufacturer's certification of stud-based weldability. And 792, responsibility for test. The stud manufacturer shall be responsible for the performance of qualification testing. Oh, well, yeah. These tests may be performed by testing agencies satisfactory to the engineer. So a third party could do the testing. The agency performing the test shall submit a certified report to the manufacturer of the studs giving procedures and results for all tests, including the information described in 7.9.10. Extent of qualification. The qualification of stud base, this is 7.9.3, shall constitute qualification of stud bases with the same geometry, flux, and arc shield, which is also the ferrule, having the same diameter and diameters that are smaller by less than 1/8 inch in diameter. So here they do give them a little leeway in diameters for qualification coverage. Stud base qualified with an approved grade of ASTM A29 steel and meets the standard mechanical properties shall constitute qualification for all other approved grades of ASTM A29 steel, provided that the conformance with all other provisions stated herein shall be achieved. 7.9.4, duration of qualification. The size of stud base with arc shield, once qualified, shall be considered qualified until the stud manufacturer makes any change in the stud base geometry, material, flux, or arc shield which affects the welding characteristics. So they're essentially qualified for the life of that design. And then we move on to preparation of specimens. So again, this is all under the 7.9 manufacturer's qualification. 7.9.5.1, materials. The test specimens shall be prepared by welding representative studs to suitable specimen plates of ASTM A36 steel or any of the other materials listed in Table 3.1 or Table 4.9. Studs to be welded through metal decking shall have the weld-based qualification testing done by welding through metal decking representative of that used in construction, galvanized per ASTM A653 coated designation G90 for one thickness of deck or G60 for 2 deck plies. When studs are to be welded through decking, the stud-based qualification test shall include decking representative of that to be used in construction. Welding shall be done in the flat position, plate, surface horizontal. Test for threaded studs shall be on blanks, studs without threads. Interesting. Not sure why they tell them to do that. So there's a little bit of complication here in the qualification. If you're going to use a stud through metal decking, it's got to be qualified according to this clause. And we move on, 7.9.5.2, welding equipment. Studs shall be welded with power source, welding gun, and automatically controlled equipment as recommended by the stud manufacturer. Welding voltage, current, and time shall be measured and recorded for each specimen. Lift and plunge shall be at the optimum setting as recommended by the manufacturer, which is a little weird because this is communicating to the manufacturer. So saying, use whatever you think is good.
Right.
And then we get into the 7.9.6 number of test specimens. So you've got a high current, you've got several different conditions. So this 7.9.6.1 is high current for studs 7/8 or 22 millimeters or less, smaller. 30 test specimens shall be welded consecutively with constant optimum time, but with the current 10% above optimum. For studs over 7/8 of an inch, 10 specimens shall be welded consecutively with the constant optimum time. Optimum current and time shall be to the midpoint of the range normally recommended by the manufacturer for production welding. So that was a mouthful. Then the next section, 7.9.6.2, is low current. And again, it subdivides it between 7/8 is the dividing line. So 7/8 or less, 30 test specimens shall be welded with a constant optimal time, but with a current 10% below optimum. For studs over 7/8 of an inch diameter, 10 specimens shall be welded consecutively with the constant optimal time, but the current 5% below optimum. So I just would have to yield to the experience. You know, the subcommittee or this task group has representatives from the prominent stud welding manufacturers on it. Nelson. I got an interesting side story about that. Anyway, so they've probably had a good hand in recommending these particular constraints on testing to cover the range, high current, low current. And then there's the next clause, 7.9.6.3, metal deck. For studs to be welded through metal deck, the range of weld-based diameters shall be qualified by welding 10 studs at the optimal current and time recommended by the manufacturer, conforming to the following. And then it has 4 subclause, parenthetical clauses: maximum and minimum diameters welded through one thickness of 16 gauge deck, coating designation G90. Maximum and minimum diameters welded through 2 plies of 16 gauge deck, coating designation G60. And maximum and minimum diameters welded through one thickness of 18 gauge G60 deck, deck over one thickness of 16 gauge G60 deck. And 4 maximum and minimum diameters welded through 2 plies of 18 gauge deck, both with G60 coating designation. The range of diameters from maximum to minimum welded through 2 plies of 18 gauge metal deck with G60 galvanization shall be qualified for welding through 1 or 2 plies of metal deck 18 gauge or less in thickness. So again, you can't use just any stud to weld through metal decking. It's got to be qualified according to this clause for that purpose. And apparently most metal decking is galvanized, so that's why they require the galvanization as well.
All right. So where does that leave us off at?
979 tests. Or 797. Sorry.
797 tests. Okay, so this is we're not gonna read through this one all the way. I think we've done more than enough, but we're gonna just basically say this is, unless you're a testing facility, a manufacturer, these are the tests for you. So these are the ones you're gonna have to do: tension tests, bend tests, weld through deck tests, retests, acceptance, etc. Now we're gonna dive into tables and the figures. So table 7.1, mechanical properties. This is the requirements for studs. Any thoughts here, Gary?
Well, here's where we get introduced to the different types. So you've got type A, B, and C with 61 KSI, 65 KSI, and 80 KSI respectively on tensile. And then it gives the yield requirements, oddly enough, for the type C, that it goes to a 0.5% offset versus a 0.2% offset. Interesting, I didn't know that. And you don't have to have elongation for type C or reduction of area. Also interesting. And then it gives them sub-notes on what type A studs are. Type A stud shall be general purpose of any type and size used for the purposes other than shear transfer in composite beam design and construction. Type B stud shall be of studs that are headed or bent or other configurations in 3/8 inch, 1/2 inch, 5/8, 3/4, and 7/8, and 1 inch diameter that are used as essential component in composite beam design and concrete anchorage design. So you got to have a type B for your anchor connection, shear connectors. Type C studs shall be cold worked, deformed steel bars manufactured in conformance with ASTM A496, having a nominal diameter equivalent to the diameter of a plain wire having the same weight per foot as the deformed wire. ASTM A496 specifies a maximum diameter of 5/8, 0.628, 16 millimeter maximum. Any bar supplied above that diameter shall have the same physical characteristics regarding deformity or deformations as required by ASTM A496. I'm not exactly sure what type C's are. I haven't seen them. I wish there was a picture.
Yeah, I've never run across them either, so I guess we'll throw them in that unicorn category. We haven't seen them, but I guess they exist, right?
And then here is the table 7.2 is the minimum fillet size that was referred to in the code language. So that's based on stud diameter. So you have 1/4 through 7/16. You have a minimum fillet size of 3/16. And I'm not going to do all the metric comparison. You can read that in the code. 1/2 inch, you need 1/4. 5/8, 3/4, 7/8 needs 5/16, and a 1 inch needs 3/8. And I guess there's nothing above that.
Right. I think because you get much bigger than that, and you just needed such a monster power supply, so to do anything above that. Moving on to figure 7.1, dimensions and tolerances of standard type headed studs. So this tells you how big the studs are going to be for the shank diameters. And then 7.2 is going to give you the typical tension test fixture, to pull it apart so that you can get a tensile strength for the material. Anything to add there, Gary, or is it pretty straightforward?
No, that's just your normal. You got to put a dimension on, a tolerance on everything, and there's a picture of a typical tensile test fixture.
All right, let's go to figure 7.3, torque testing arrangement and table of testing torques. Fire away, Gary. I know you got some stuff to say here.
Well, so this has to do with not torque to destruction, but the torque pre-production testing that you would need to know. And there's a lot of faults here because it does mention something about lubricant. So in the note under there, it says dimensions of test fixture details should be appropriate for the size of the stud. Well, duh. Yeah, you got to have a collar long enough so that you're not turning the screw, past the threads. The residue set shall be clean and free of lubricant other than the residue of cutting cold forming lubricants in the as received condition from the manufacturer. So if you are a mechanical engineer, you know better than me all the differences in tension that can be. So what you do, you're applying tension through torque. You're not actually putting a twisting force on that stud to base metal connection. You are actually trying to yank it out of the plate. And if you have more lubricant, then a lesser amount of torque will apply a greater amount of tension, and then drastically so. So they're saying it shall be clean and free other than what was used to produce it. Again, I'll have to yield to the expertise of the stud manufacturers that are typically on these sub-task groups that this is sufficient to cover that. And the other thing is, as you know, torquing devices can go wildly out of calibration. So you need to make sure that you're measuring it accurately with calibrated equipment.
Yeah, and like you said, you're just cranking on this thing, trying to get it to pull out. You're just doing a tensile test in place, and you're not necessarily getting numbers. But
no, this is not for destruction. This is, if you reach this torque, it's below the destruction threshold.
Oh, all right, my bad.
This is for the pre-production testing, because in the qualification testing, it just said torque it till it breaks. It didn't refer you to this table or mention a specific torque.
Right.
And that was just the option of, bending, tensile testing, or torquing. You could use any of those, and it's just try to testing to destruction.
All right, and then we go to figure 7.4 bend testing device. This just shows you what the bend testing device looks like, gives you an idea. And 7.5 is suggested type of device for qualification testing of small studs, just some drawings and whatnot to go off of. So that wraps up Clause 7. So that pretty much takes us through Clause 7. You got anything else to say on finishing up Clause 7 on stud welding? Any words of wisdom on our way out the door on Clause 7?
No, just that if you ever get into a situation where, the clause isn't clear, submit an inquiry. You can actually call the switchboard at AWS and ask to talk to a technical person. You have an inquiry, and they will often answer your issue on the phone or email. Just contact, and it's a different person as time goes by, so I won't give you a name, and I don't have their emails, but just contact the AWS switchboard and tell them you have a technical inquiry, you want to speak to somebody, and they'll get you connected, and you can get an answer to your issue.
All right. Well, thanks for joining us to talk about Clause 7 there, Gary.
All right. Well, thanks for having me. Appreciate it.
All right. So that ends Clause 7.
That wraps up Clause 7 of AWS D1.1, stud welding. I'd like to thank Gary Martin for joining us for this episode. Really appreciate him stepping up and giving us a hand finishing out that episode. If you have any questions or comments, please contact me at gpacex@gmail.com. Heading forward, we're going to be finishing up AWS D1.1 in the next few weeks, and then I don't know what direction the podcast is heading. If you have any episode suggestions or any subject topics that are code related that you want us to touch on, please feel free to contact me. Another advertisement on the way out the door. If you're on a budget and looking for an online CWI course, check out train-eng.com. The Part A online course is $149. Part B of the CWI course is $129. Train ENG also has the CWI course split out so that if you only have a few areas that you would like to brush up on, they have it cut out buffet style. One of the buffet style options is for modules 6, 8, 9, and 10 of the CWI review course. This covers Module 6, Metal Properties and Destructive Testing, Module 8, Welding Metallurgy, Module 9, Weld and Base Metal Discontinuities, and Module 10, Visual Inspection and NDE Methods. All of this material is covered for the low price of $75. Also, if you just want questions, the CWI Part A question bonanza is $40. Anyways, check out train-eng.com. Thanks for listening to the Welding Codex.